they kind of tie in with some things we talked about, but are also kind of their own thing as well. Systems of equations kind of fall into the linear equations and the lines that we talk about as far as the topics that we've seen already. I usually save it to the end though, because at this point we need to be reviewing how to handle this stuff anyway. So this is a great review of dealing with graphing and solving, all right, as we prepare for the final. What you're going to see here though is a system of equations is dealing with what happens when we have not just one parameter, but maybe two or more parameters that help affect the situation, okay? Oftentimes there's more than one thing that affects what's going on. Right. If you think about the vending machine we brought up, you have the cash input, you have the digital clicking of a button as far as dealing with the selection choice. And then there's so many different things that kind of get tied together. Well, pricing of that item is another thing that can get thrown in there, where it's like when you consider the cost of running the electricity through the machine, bringing the drink to the machine, right? Making the drink, there's a lot of things that can come in here. And this is where systems begins to be something that helps us. Now, we're just doing a very basic perspective, of course, right? We're looking at linear equations. So this first problem here is taken into perspective of what do we do to solve a system of equations with two linear equations, right? Well, the first place to start here is let's look at it from a graphing perspective. So we have two lines and we need to graph both. How can I go about graphing this first line, or what's a good strategy to use here? You could definitely get y by itself, right? Understand when you get y by itself, though, you're going to be doing more work than you have to. Nothing's wrong with that, though. If you solve for y here, it'll be just like this next one, but what do we focus on? If I have it y by itself, what can we use here? What are the two things you can identify when you have y equal to 3x minus 3? All right, so we look at it from y equals mx plus b, right? Where the slope is our m value, right? And the y-intercept is the b value. Now keep in mind that it is an ordered pair. The idea is if you plug in 0 for x, you get that. So you could definitely take the first one, solve for y, and take that approach. I'm gonna go ahead and plot this out though, since we have it. So 0, -3 is the first point I'm putting here. The thing is, for the slope though, we should write it as a fraction. Why would I write that as a fraction? It helps us highlight though the rise over run. Is that clear to everyone? That would definitely be the focus that I want to make sure you see here is this is the rise, this is the run, the change in x over the change in y, which would be the more proper way. The rise over run is perfect. With that said, then, as we look at this problem, that means I need to go up 3 over 1, and that will be another solution on that line that I'm drawing. Do I need any more points? Or can we draw a line now? All right, so technically speaking, 2 points is all you need to draw a line, but make sure you see there, that's the nice thing about having y by itself. That's a great way to solve using slope and intercept, okay? Now, the other strategy that, be careful, this will be something that just tells you to do it, right? There's gonna be times like you saw on my test where it said, hey, find intercepts, right? But that's also something else. Whenever you see x and y on the same side here, and then you know it's a line because there's no exponents and this is a constant value, finding the intercepts is a great approach too. What I mean by that is, hey, let's let x equal to 0 and we're going to solve. And then after I do that, let's let y equal 0 and solve. This will give us two ordered pairs where I'll have 0 comma some value and then some value comma 0. All right, so if I let x equal to 0, that'll give us 2 times the 0 minus 3y equal to -12. So -3y equals -12, which will give us what, y equal to 4. We good with that? Questions or concerns? The nice thing is there, as long as you're careful with your signs, right? Don't drop the negative on the -3. It's just a quick division usually. And this is for the lines though, of course. So that'll give me 1 point where we're saying, hey, 0, 4, I can put a point. I can do the same thing the other way though, but make sure you see here if you wanted to, you could just be like, hey, this is 2x equals the -12. So x equal to -6. Which will be right there. Okay. Now I go through and draw a line through those 2 points. And it will look something like that. All right, so this is 2 separate lines that we've drawn. So is there any concerns about graphing either of the lines there, whether it's the intercepts or the slope and y-intercept? Now, if I'm saying this is a system of equations, that these lines belong together for some purpose, what point should stand out to us? When you look at these 2 lines, what's something that you notice about them? They intersect each other. Thankfully here, it happens at a nice integer value. That's not always going to happen, okay? But here we have a nice integer value. What's that going to be? 3, looks like 7, no 6. All right. That's going to be what we call a solution to a system of equations. Any ordered pair that is a shared solution between every equation involved is the solution to the system itself. All right. And oftentimes that's our focus is where do these equations intersect or share that solution? In this case, it's an ordered pair solution because we have X and Y. All right. Any questions with that being a focus? All right, so the next thing is if I give you a system, right, can we determine if a point is a solution? So here we have two different systems. So I have the systems here, and you'll see I just kind of write them in a stacked order, and the context would be like, hey, this represents a system of equations, right? Context is very important here. So I'm giving this context that this is a system of linear equations, and I want you to determine if the ordered pair right below it is a solution or it is not. So write that down and then let's see if they are solutions. You could, yep.
So to schedule that retest, do we just go to the testing center and just like?
You need to go on the BRCC's webpage to the testing center, and there will be a link to schedule an exam. You need to do a 90-minute instructor exam.
Okay.
Yeah, so if you plan on trying to redo one of the tests, you have to make sure though, make your appointment, do what? Forward me the confirmation email. So when you get the confirmation email, forward it to me, but you also need to put in that confirmation email, a little message like, hey, Mr. Green, here's my confirmation email. I plan on taking exam 1, 2, or 3. You have to make sure to declare to me what exam it is because I'm going to go over to them and set up the proper exam. So if you don't tell me what exam it is, it's not going to work out. You have to tell me exam 1, exam 2, or exam 3. Pick the one that you want to do. Let me know in that email so I can go drop that off with them. I decided just do a paper test. That way it's not different from what we've been doing. Okay. Same format, easy on them, easy on y'all, because you already know what to expect. Is that clear to everyone? And I encourage you, hopefully you have the old test, so look over it, right? It's not going to change a lot. Now, with this system, with both of these systems here, how do I determine if an ordered pair is a solution to the system itself? What do we need to do with the ordered pair to determine if it is or is not a solution to this system? Plug it in, right? How many times do I need to plug it in though? twice, right? We have to plug it in both equations, right? Because the solution to a system is when it's a solution to each equation individually, okay? So what we want to do is go to the first equation and plug it in. 5 minus 0 equal to 5. Well, look at that. 5 definitely equals 5. So we're good there. Then we need to go to the next equation. 2 times 5 plus the 0. And once again, we get a true statement. Because those are both true statements, right? We can confirm that this is a solution to the system. And make sure you see here, though, the context, again, is very important that we're working with a system of equations. Now, one thing I will point out, sometimes you might see like a little curly bracket out front. That's just another way to say, hey, these belong together for whatever purpose we're working on, okay? If you remember, we saw that similar kind of notation with piecewise functions. So keep that in mind. My context here is I put the word system. Any questions there? All right, so the next one, right? Let's plug it in and see. Do I need to go any further? The first equation, it's not a solution, right? At that point, we know it doesn't work for the system. To be a solution to a system, that ordered pair must be a solution to each individual equation. And we just found here that it didn't work with the first one. So this second situation, we'd say, is not a solution. Okay. We're good with that, though, as far as plugging in to check them. Now, with that said, how many solutions can we have if we know we're looking with lines? So is there any way I can draw another line on here that would create more than one solution between two lines? How so? So if we know both of them are straight lines, can straight lines intersect more than once? Not necessarily, right? The part we have to be careful of is what happens when the two lines are what? Parallel, right? That's going to be a special case. You'll also find if two lines are parallel, there is a small chance that they're the same line. So keep that in mind as well. But we should expect a single ordered pair here unless they're parallel, then we have some exceptions. So keep that in mind. And we'll talk about that if we have time. That's one of the ones I'll talk about in briefly tomorrow if we need to, okay? But what we want to look at is, hey, how do I find the solution to a system? The first thing you need to make sure to highlight here is the graphing that we did the first problem. Graphing is a great way to find the solution to a system. However, it really is only nice when you have, like, say, integer solutions that you can clearly identify. All right. If you're using software, graphing and allowing the software to tell you where the solution, that's fine as well. But that's not what we're doing, right? We need to know how to do this through other means as well. So the first mean here is going to kind of focus on how these equations are written. So what does someone notice about one of the equations that you're writing down here for this system? One of them has y by itself, right? Now, is that how these were written? No, these were in that standard form, right? Where this one of them's in slope-intercept form. Nothing's wrong with that, right? They're both lines. That's perfectly fine. What you're going to find is, this is a great time to use what we can call substitution. All right, and what do I mean by this, right? So using substitution says, hey, I already know what y is equivalent to. Y is equivalent to 2x minus 3. So I can take that and say, hey, let's go to the second equation that we're working with here. And let's, instead of putting y, put the 2x minus 3. Now, keep in mind, this is still y. We're just taking it and putting what was opposite in place there, okay? The reason we like that, though, is now we only have one variable here. With one variable, we can go use our solving skills that we've used in the past. Now, the part you want to be careful of with this problem, of course, is distributing that negative. We can then combine like terms and get x by itself. Now, everything was focused on the fact that here was what we said y was, so I plugged it in for the y value. This was the y value before, okay? Now, the other thing here, make sure you see, is I took the first equation, I plugged it into the second equation. That's also a big thing here. If you try to do something different, you'll get just identity situations. So we have to be careful. With this said, am I done once I get x equals 2? I got to plug in x. Now, does it matter where I plug the x in? Right. Remember, it's a shared solution, right? So when I plug 2 in, I better get the same y value no matter which one I use. Now, hopefully you see here, it's probably better to use the first one, right? It's nicer to plug into slope-intercept form, because at that point, it's like, hey, 4 minus 3 is 1. So that at that, we would have our solution. But if you prefer, you could definitely use the second equation. Which, as you see there, negative y equals negative 1 would bring us right back to y equals 1. Okay. Highlighting the fact that we do have a shared solution. Now, as I mentioned, though, make sure you see here, this was nice because it was already set up that way. And that definitely made it, hey, if I have this on the final, one of them solve for y, let's just plug that in and go. All right. Any questions there? All right, here's another situation, though, that it's nice to recognize and use. But as you write down this system, make sure you see they're both in that standard form, okay? They're no longer in slope-intercept form. You technically could use substitution, but that would require you to be like, hey, let me go solve one of these equations for y. But that's going to get a little messy. Not impossible to use, but you're going to have to deal with fractions. It's going to happen, right? So keep that in mind, that as you do this, you can still solve for y and use substitution every single time you solve. Nothing's wrong with that. Substitution is definitely great. But what does someone notice about these two equations? Does everyone see how the y's kind of work nicely here? That if in some way we could take the first equation and add it with the second equation, that would be 0, right? Well, guess what? We can do that, right? We can say, hey, let's add these two equations together. And what we'd actually get is like 2x minus 3y plus x plus 3y. On the other side, though, make sure you see you would have to add the 7 and 2. Okay, now what I like to do is just kind of do it vertically. Like, hey, let's just go downwards. So 2x plus x is 3x. That would be the 0 if we just add them together. And then over here, we get 9. Now, if you write it out in the more linear fashion, the same thing will take place. Okay, so keep in mind, doesn't matter which way you write it. I'm going to follow this approach more often. So keep that in mind. One big thing here is make sure you combine like terms. That's definitely an important part, is keeping up with your like terms. But you'll see here, this one gives us, hey, x equal to 3 is one of our solutions. And then from there, it's just plug it in and find your y value. Now here, both equations are pretty similar, right? I'm going to use the second one because y is already positive. That's going to be my only reason there. So let's go plug this 3 in. Subtract the 3 from both sides and do our division, okay? Just make sure you remind yourselves though that this is an ordered pair. You found an X value, you found a Y value. Make sure you put them together. Say this is an ordered pair solution. They belong together. It wasn't just two random numbers that we just happen to write down. Now, one thing I would make sure to point out here is make sure you see these two, they were set up nicely to just jump straight into something, right? So this one, hey, slope intercept, let's just do substitution. Look at that. Those drop out nicely right off the bat. If I just add them together, -3 + 3 is 0, and I can move forward. Okay, it's not always going to be the case, but those are definitely things to keep an eye on. Okay. Is there any question with either of them, substitution or what I'm going to call elimination? The idea is we eliminated the y's to move forward. The addition, I think the textbook calls it the addition method, which, you know, when you add negatives, you get 0. So just a different terminology, the same idea. All right, so this brings up another problem then, like what in the world do I do when it's not that straightforward? Okay. Now, I will say the substitution method, as I mentioned before, you could easily solve one of these for y. So if we take this first one and solve it for y, it would give us what? Y = 3/2 x - 2. And you could plug that in and move forward. You could definitely do substitution here, but just keep in mind the idea is there's going to be work here. You have to do all the work to get there and then plug it in. Okay. I'm going to focus on the elimination method because of the fact that, hey, if you can do the substitution method, then just know that means you do the work to get here and then then plug it in as you saw before for the y value in the other equation. Okay. The nice thing is, hopefully you'll see here, when you do this, you should expect it to work out to a number you know that will work for the solution. Okay. In this case, we're probably going to end up with a fraction, but it should be a nice solution. Okay. Now, from an elimination standpoint, this isn't set up right away either, though, right? So whether you deal with a fraction or we deal with having to manipulate stuff, we have to do something. Okay. So I'm going to focus on the elimination perspective rather than the substitution perspective. What we can see here is that, hey, with some multiplication, right, I can change what I see here. For example, between 3 and 5, what is the least common multiple? So what is the smallest number that 3 and 5 both go into? Right, so the least common multiple of 3 and 5 is 15, right? What about 2 and 3? Right? Those are both numbers that, hey, if I can get that up there, would make this work really nice, right? Does it matter which one I pick? No, right? To understand what we saw here, it just happened to be the y canceled out, right? It could be the x that cancel out. It doesn't matter which one cancels out, right? So understand that when you take the elimination approach, right, just pick a variable and run with it. Now, again, this is going to be one of the more involved problems when it comes to it because really nothing works out nicely here. So we have to just make a decision and move forward. That's why I say make sure that if you're comfortable substitution, focus on substitution. If that's what you're good with, that's fine. Just know that sometimes can be a little bit more work because of fractions. That's the main thing, right? If you're comfortable with the elimination, make sure you practice that and move forward. I will say this though, if you're going further in math, elimination becomes a little bit more frequently used than the substitution, okay? Especially when you say you have 3 variables, right? We're working in a third dimension, you're definitely going to prefer elimination than substitution. With that said, I'm going to focus on 2 and 3. 6 is smaller than 15. That's my main reason. What that means is, hey, if I can treat this kind of like what we do a fraction, getting a common denominator, I can set this up to where it works nicely. For example, I could take the first equation and multiply the entire equation by 3. And I'm just using kind of the shorthand notation. The one with a circle around it is me saying the first equation. I'm putting the 3 there, say, hey, let's multiply the whole thing by 3. That would then give us 9x minus 6y equal to 12. Well, if I'm multiplying the first equation by 3, we need to multiply the second equation by 2. So if we distribute that through, 2 times 5, 2 times 3, and 2 times the 1. All right, make sure you see distribution. I had to multiply it to both sides. Whatever I do to one side of an equation, I do to the other. But now we can rewrite our system and it will look like this. Now, the tough part here is this is where the elimination approach is helpful. What's -6 plus -6? It's -12, right? So understand here that the book might tell you to multiply one of these by a negative value to alternate the signs. That's the only thing different. So what I'm telling you is, hey, if they're the exact same number, instead of adding, we can use subtraction, right? So what we want to do now is to say, hey, let's take the first equation and subtract the second equation from it, right? So what is 9 minus 10? -1, right? -6 minus -6 is any.
Oh, no, no,
Yeah. What is a number minus itself, y'all? 0. So -6 minus -6 is 0. That's gone, right? And then we'll have over here, what, 14? Being careful with our negatives, right? 12 minus -2 is the same as 12 plus 2. With that said, all they have to do is divide both sides by the negative, and we get -14. Now, if you don't like that, just as I said over here, instead of multiplying by +2, multiply by -2. You'll get -10x plus 6y equals to 2. And it's the same thing that we just said we were doing. 9 minus 10, -6 minus -6, and 12 minus -2. Yeah. No, and that's why I said, if I remember right, the book calls it the add method or addition method, and you'll see this is the approach they'll take. Okay, so if you don't like the subtraction that I'm doing here, just multiply by -2, put the subtraction there. Why do we like that? What's going on with those numbers now? One's negative and one's positive. A number plus its opposite will always be 0, okay? Now, with that said, though, we're not done, though. We do need to plug in the 14, so let's go plug this in. So 3 times -14 minus 2y equals 4. So it's at -42 minus 2y equals 4. -23. So through all that work that we just did, which definitely is not a lot, we've seen a lot more work, but as you see, this is more involved than the first two. But through all that, we found that we should get -14 comma -23. So what is special about that ordered pair we just wrote up here? What makes this one unique from any ordered pair we can think of? There's a lot of double negatives, right? That's all of quadrant 3, right? When I look at this system, though, what makes this set apart from every other ordered pair? What were we doing just now? What's the direction say? We're trying to solve the system, right? When we're trying to solve, we're trying to find a solution, right? A solution means that when I plug it in, it makes the equation what? True, right? Make sure we go back over here. We plugged this in to both equations, and both times it gave us a true statement, right? So this ordered pair was special because it was the solution to a system, right? From a graphing perspective, hey, whatever these lines look like, we just found where they intersect. Okay. When I look at this here, it makes you understand that this point is special because, hey, that is the shared solution of both of these equations. Hence why we call it the solution to the system of linear equations. Okay, we want to make sure to highlight that when we deal with those, okay? Any questions there? All right, so we need to look at a special situation, though, so let's look at another one. All right, so here's another system. What stands out to someone as we go to solve this one?
Oh, it's
Y by itself or slope intercept form, right? Solve for Y, slope intercept form. Okay. What's a great way to solve this one? Substitution, right? Now you can set up elimination, right? If you wanted to, you could just undo this by saying, hey, let's subtract 3x from both sides. So if you really like the elimination approach, set it up that way, move forward. Okay. But my focus here was definitely going to be the substitution. So here we'll say, hey, it was solved for Y, so let's go plug it in for Y. Which means be careful because sometimes it could be solved for X. If it's solved for X, plug it in for X. Now, with that in mind, when I go to solve this, what happens? I didn't get 0. Is it wrong if you have both sides of 0 though? No, you just did an extra step is all it is. Okay. Now, this is special because what that means is when I deal with this, these lines had something in common, right? Specifically, the slope is in common. If two lines have the same slope, we say that those lines are parallel, right? I think we spent a couple minutes in class on that, but just remember parallel lines have the same slope was the key there. All right. When that happens, right, we have two different situations that can occur. This first one here that I've given you, we got a true statement here. That's going to be the important part. If you get a true statement, what we want to do is say, hey, there's infinite solutions. What did I not write just now? I did not write all real numbers. Does everyone see that? What is our context right now? We're working in systems, right? We're looking for ordered pair solutions. If you say all real numbers, that doesn't fit the ordered pair that we're working with, right? All real numbers for what, right? Remember, we break it down the domain and the range. We have X and Y values. So we have to make sure that we're clear on this. So what we're going to see here, this is a situation where we're going to have an infinite number of ordered pairs that are the solution. And the approach that you would take for this would be like, hey, as long as it meets this particular pattern, it is a solution. So when we get here, we're going to focus on Y equal to 3X minus 2. And we're going to say, hey, let's look at T, which is an element of the real numbers, right? This is me just, we'll have to look at a problem to make sure we see on the homework. I picked some random letter though. Everyone's clear on that? The assignment will tell you what variable to use though. Okay, make sure you use the variable they say. The important part here though, what did I put first again? Infinite solutions, right? So every ordered pair though is always going to be the situation where we're going to let x equal to t. Well, if we let x equal to t to get y value, we got to plug t in. And the nice thing about this is we already had y by itself here, right? So that would give us 3t minus 2. That would be the format for every solution. Okay. Now keep in mind, as you see there, that's the equation basically that we started with. What you're seeing here though, the all real numbers is being assigned to the domain, right? We're saying all real numbers for our domain, but our output must follow that 3t minus 2. Okay. Now, is this going to happen all the time? No, this is only when I try to solve and I get a true statement, no variables left over, whether it's 0 equals 0 or here I have 4 equals 4. If you get a false statement instead of a true statement, like, so if you do all this work and you get 3 equals 12, what would you conclude? No solutions, right? So that doesn't change. The only thing that really changes here is this little aspect there. Because we're working in systems, we don't want to jump straight to all real numbers. We acknowledge that there's infinite solutions, and we assign that to the domain of the possible solutions. That's going to be the big difference. Now, the tough part there is keep in mind, like if I brought in different functions, there still would be infinite solutions, right? So that domain should always represent whatever I'm working with. Now, for our perspective, though, again, we're only going to do lines, okay? This does not happen all the time, but it can happen. Any questions or concerns there? Now, make sure you do those assignments. They should be open. If not, please let me know, but everything should be open there so that we're comfortable with this. I would encourage you to go get it done today. That way you can study for the final, right? Now, as we finish up,